Good day, we are Mark Edward Gonzalez, Lorene Uy, and Dr. Joel Ilaw from De La Salle University, Philippines. We will be presenting our research entitled Designing a Lightweight Edge-Guided CNN for Segmenting Mirrors and Reflective Surfaces. Despite having mirrors and reflective surfaces all around us, existing computer vision systems have difficulty detecting them due to the lack of consistent appearance and the visual similarity of reflections with the surroundings. This complicates several tasks, with Zhang et al. Having to augment visual information from cameras with cues from external sensors to accommodate for mirrors. Furthermore, mirrors pose potential hazards to autonomous driving systems that rely on stereo vision since they can cause glare spots, irregularly distorted reflections, and infinite reflections. These challenges are pronounced given the presence of safety mirrors in roads and parking spaces, as well as large reflective surfaces in the facades of high-rise buildings. Hence, developing systems that can reliably localize them is critical to autonomous navigation. While general segmentation frameworks have achieved success in various applications, they are unable to adequately distinguish reflections from the actual objects. Reflections also get segmented. Meanwhile, salient object detection techniques may not necessarily tag mirrors as salient. Therefore, segmenting mirrors and reflective surfaces is a challenging task that requires tailored approaches. Existing works in this area focus on exploiting contrasts, relationships between the inside and the outside of the mirror, edge features, and semantic associations. Most have ResNext 101 as their backbone and have over 100 million parameters. The gaps we attempted to address are as follows. Existing datasets are mostly limited to clear mirrors in indoor scenes. Outdoor mirrors and reflective surfaces, such as tinted car windows and building facades, are not well represented. Most mirror segmentation models have over 100 million parameters. This may prohibit their use in resource-constrained devices like drones. Designing lightweight models remains an unexplored direction. In an attempt to address these, we propose a dataset of 454 images of outdoor mirrors and reflective surfaces. We modified the architecture of the PMD net and extensively tested different backbones and edge-related modules to guide the segmentation. We also pruned our best-performing CNN, resulting in a lightweight model that performs competitively with the state of the art. We used two publicly available mirror datasets, MSD and PMD. MSD consists of 4,018 images. However, most are zoomed-in images of indoor scenes with high similarity. PMD sought to address this by aggregating 6,016 images. Although the images are more varied, outdoor mirrors and reflective surfaces remain underrepresented. To help address this limitation, we proposed the De La Salle University Outdoor Mirrors and Reflective Surfaces dataset. In total, our dataset contains 454 images with an average structural similarity of 28.67%. The leftmost figure shows the mirror location distribution in our proposed dataset. Yellow corresponds to higher frequencies, while blue corresponds to lower frequencies. It can be seen that most mirrors are located near the center. The middle figure shows how big the mirrors are versus the whole image. Most mirrors occupy up to 20% of the image. The rightmost figure shows the color contrast between the reflection and the surroundings. The color contrast of most images is below 40%, which suggests that the reflections are similar to the surroundings, thus making our dataset more challenging. Our proposed dataset has 454 images and a total of 786 mirrors within those images. 45.17% of these mirrors are irregularly shaped and almost a quarter are occluded by another object.
Our base model is PMDNet. Its main components are first, the RCCL or Relational Contextual Contrasted Local Module for extracting both contrasts and similarities inside and outside the mirror. And second, the EDF or the Edge Detection and Fusion Module. We introduced two modifications to PMDNet in an attempt to improve its performance and lower its complexity. First, we changed its feature extraction backbone. The base model originally uses rest next to 101, but we explored 7 feature extraction backbones pre-trained on ImageNet, as enumerated on the slides. Second, we modified the edge detection and fusion module of PMDNet. To extract low-level edge features, our design connects the side output of the lowest level backbone to 4 parallel convolutional layers of varying kernel sizes and dilation rates, replacing PMDNet's original 3 sequential convolutional layers. To extract high-level edge features, we share PMDNet's use of a convolutional block attention module, a lightweight module that infers spatial and channel attention maps. To fuse these low-level and high-level edge features, we expand PMDNet's edge prediction module from a single 3x3 convolutional layer to a 1x1 convolutional layer with batch normalization and ReLU connected to a 3x3 convolutional layer. In summary, our modified architecture aims to exploit richer edge semantics without adding significant overhead to the model's complexity. We set the initial learning rate to 1 times 10 raised to negative 3 and the optimizer to stochastic gradient descent. We also proposed our compound loss function consisting of 3 loss functions. First, intersection over union or IOU loss was used to supervise the training of the multiscale feature maps, that is, excluding the final mirror map. Second, a Laplacian-based loss for emphasizing edges was used for the boundary map. Third, an additive loss that combines the weighted IOU and binary cross-entropy loss was used for the final mirror map. We differ from the usual approach of employing Lovász softmaps for the mirror map and BCE for the boundary map. IOU is a lot less expensive than Lovász softmaps, although it is generally outperformed by the latter. To compensate for this, we apply weighted IOU and BCE to supervise the training of the final mirror map to draw the model to a larger receptive field. Meanwhile, our Laplacian-based function addresses BCE's sensitivity to imbalance edge-non-edge distribution. It is important to address this since our module is concerned only with mirrors' edges. To further decrease its complexity, we subjected our best-performing model to filter pruning via geometric median, a one-shot structured pruning technique that reduces redundant filters by using the geometric mean to capture the mutual information shared by the filters in the same layer. We evaluated the performance of our models on 3 test datasets as listed on the slides and based on 2 metrics, maximum F measure and mean absolute error. Going to our results, we benchmark our model with VST, a state-of-the-art transformer-based salient object detection model that can handle scenarios with similar foreground and background, which is the case for most images with mirrors. We also benchmark with our base model, PMDNet. Our model that uses efficient net and employs our compound loss function and edge extraction and prediction module performed competitively with PMDNet. It also has the advantage of having 4.79 times fewer flops and 2.77 times fewer parameters. The pruned version of our model also performed competitively with PMDNet and registered the highest F measure on both MSD and DLSU OMRS. Among all our models, it had the least complexity, with 78.20 times fewer flops and 238.16 fewer parameters. Although our model with an efficient net light backbone was not able to outperform PMDNet, its F measure scores across all 3 benchmark datasets were consistently within 0.06 points of the highest scores. Together with the previous results, this suggests that the efficient net family is a promising and less computationally expensive alternative to the ResNext backbone used in existing mirror segmentation models. We now go to a qualitative comparison of results. As seen in the boxed column, salient object detection models may not necessarily tag mirrors as salient. Our best performing model is capable of handling some challenging cases. This includes images where both the actual object, including the mirror, and the reflection occupy a large portion of the image, or where the reflection has a similar color with the mirror's frame. Our model is also able to handle some cases where multiple mirrors and reflective surfaces are present. By the way, the images you see on the screen are from our proposed dataset. The pruned version of our model was able to segment irregularly shaped mirror shards. Although in general, it seems to have some difficulty handling cases where both the object and the reflection occupy a large part of the image. Analyzing the effects of pruning, we found that further increasing the sparsity to 40% already resulted in a large drop in accuracy. In the figure, we see that at 30% sparsity, the pruned model already fails to distinguish the hung face mask from the mirror. Although the F-measure scores were comparable before and after retraining, there was a large increase in MAE prior to retraining due to output maps emphasizing the mirrors but failing to completely mask out the surroundings. We also analyzed our model's components. Our edge extraction and prediction module helps capture boundaries of small objects that may otherwise be missed, as seen in the first row. However, it may also include a bit of noise, as seen in the second row. With regard to our choice of loss functions, our compound loss function resulted in the most accurate mirror map in the first row, although in the second row, we see an increased sensitivity to boundaries near the reflection's chest area. The overall contour of the ground truth mask was better captured. Finally, we discuss our model's limitations. Since our model exploits discontinuities and similarities, it has some difficulty handling cases where the contextual features appear continuous, or where the available features are not enough due to the mirror occupying the entire image. Sharp discontinuities may also cause the reflection to be treated as part of the predicted mask's boundary. Small mirrors in the background may be hard to recognize, and the same goes for heavily tinted reflective surfaces. Fine details such as cracks are also not preserved. And some failure cases are challenging even for us human observers.
In this research, we proposed DLSU-OMRS, a dataset of 454 images of outdoor mirrors and reflective surfaces, which are not well represented in existing datasets. We also modified PMDNet and extensively tested different backbones and edge-related modules to guide the segmentation. Our best performing model uses EfficientNet V2 medium and employs an edge detection module with parallel convolutional layers and a lightweight convolutional block attention module to capture both low-level and high-level edge semantics. Our model registered F-measure scores of 0.8483, 0.8117, and 0.8388 on MSD, PMD, and our proposed dataset. Compressing it by pruning via geometric median resulted in scores of 0.8498, 0.7902, and 0.8456, performing competitively with the base model, but with 78.20 times fewer flops and 238.16 fewer parameters. Thank you for listening.